Hello and welcome to another episode of Twiml Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. A big thanks to everyone who participated in last week's Twiml online meetup, and to Kevin T from SIGOP for presenting. You can find the slides for his presentation in the meetup Slack channel, as well as in this week's show notes. Our final meetup of the year will be held on Wednesday, December 13th. Make sure to bring your thoughts on the top machine learning and AI stories for 2017 for our discussion segment. For the main presentation, prior Twiml Talk guest Bruno Gonçalves will be discussing the paper Understanding Deep Learning Requires Rethinking Generalization by Shiyuan Zhang from MIT and Google Brain and others. You can find more details and register at twimlai.com/meetup. If you receive my newsletter, you already know this, but Twiml is growing and we're looking for an energetic and passionate community manager to help expand our programs. This position can be remote, but if you happen to be in St. Louis, all the better. If you're interested, please reach out to me for additional details. I should mention that if you don't already get my newsletter, you are really missing out and should visit twimlai.com/newsletter to sign up. Now, the show you're about to hear is part of our Strange Loop 2017 series, brought to you by our friends at Nexosis. Nexosis is a company focused on making machine learning more easily accessible to enterprise developers. Their machine learning API meets developers where they're at, regardless of their mastery of data science, so they can start coding up predictive applications immediately, and in their preferred programming language. It's as simple as loading your data and selecting the type of problem you want to solve. Their automated platform trains and selects the best model fit for your data, and then outputs predictions. To learn more about Nexosis, be sure to check out the first episode in this series at twimlai.com/talk/69, where I speak with co-founders Ryan Seavey and Jason Montgomery. Be sure to also get your free Nexosis API key and discover how to start leveraging machine learning in your next project at nexosis.com/twiml. In this show, I speak with Soumith Chintala, a research engineer in the Facebook AI Research Lab. Soumith joined me at Strange Loop before his talk on Pytorch, the deep learning framework. In this conversation, we discussed the market evolution of deep learning frameworks, different approaches to programming deep learning frameworks, Facebook's motivations for investing in Pytorch, and much more. This was a fun interview, and I hope you enjoy it. And now, on to the show. Hey everyone, I am here at the Strange Loop conference in St. Louis, and I'm with Soumith Chintala, who is a research engineer at FAIR, the Facebook AI Research Lab. And Soumith is giving a talk here at the conference tomorrow and graciously agreed to spend some time with us to talk a little bit about what he's up to and about his talk. So welcome, Soumith.
Hi, Sam. Nice to be here at Strange Loop for the first time.
Absolutely. And welcome to St. Louis. So why don't we get started by having you tell us a little bit about your background and how you got into AI research?
Sure. Let's see. About 8 years ago, I wanted to be a digital artist, trying to make VFX for movies and stuff. I did an internship there, and as soon as I went into that internship a weekend, I realized that I was terrible at this. I was not an artist by any standards. And then I had to find second choices in life, and I was looking at my interests, and one of the things that struck to me was I was a decent programmer since a young age. Mm-hmm. And I kind of like the whole computer vision angle, object detection. You know, you show a picture and some machine tells you, oh, there's a person here, there's a cat here. That just fascinated me. So I went down that line. I did a small internship at a research lab in India at this place called IIIT. And like there I did a little bit of random stuff. You know, as an undergrad, you explore all kinds of things. Yeah. And I tried a little bit of face detection and a little bit of taking a bunch of pictures of a monument and then stitching them together in 3D.
Okay.
And I had no idea what I was doing. I was just like trying to put together things based on various tools and snippets. And you know how you call programmers Stack Overflow bots, you just take snippets and you try to put together something. And I was
guilty as charged.
Guilty as charged. And then I got an opportunity to come to CMU in Pittsburgh.
Okay.
Just doing more exploration, trying to figure out what I want to do. There I got to play robot soccer. So program robots to play soccer.
Autonomously?
Autonomously.
Nice.
So you basically like flash the robot with your program and then they just play soccer.
And I've seen pictures of a variety of scenarios. Are these the humanoid ones?
Yes, the ones I worked on were these humanoid ones.
Okay.
They were called Naoki robots, Naoki. And they were, I came in with the expectation that we figured out so much in robotics, we must be pretty good.
Uh-huh.
And we couldn't make them stand properly. Like they would just stand, they would walk, and they would fall down, and that's the state of the art. If you could make them walk without falling down.
We've probably all seen the video, the Boston Robotics robots that like tries to turn the doorknob handle and just like falls over totally.
I saw that one. So that like shocked me because I was like, oh, robotics was so much more advanced than it is. And it also, I saw opportunity there. I'm like, oh, this field is still kind of open. And we were trying to do the whole algorithm of the robot playing soccer with vision. Like, oh, can you identify where the ball is and walk towards it and stuff? And that part as well was very, very rudimentary, not working very well. It's like it would sort of look for an orange pixel in your image and try to make that pixel bigger.
Okay.
And even something as stupid as that, it wasn't working very well.
That's pretty funny.
So I did a bunch of random stuff there, and I had a good time at CMU, and I decided I want to go into artificial intelligence, computer vision, robotics. And then I applied to a bunch of places, CMU being one of them, and I didn't get accepted anywhere. And I was looking for late applications and stuff, and that also combined with someone where there was computer vision. And I saw this webpage by this guy called Yann, and he had a janky webpage with some, with some object detection stuff going on. But I was like, hey, it's NYU, I'll give it a shot. Yeah. So I applied to NYU and a couple of other places, last minute because I got rejected from all of my top schools I wanted to go to.
No offense, Yann.
I told him the story right away. And I got accepted to NYU, got in, wasn't super happy with myself because I was like, oh, I can do so much better if I worked harder. And then it gets even more hilarious. I come into NYU, I email Yann beforehand. I'm like, hey, I did a little bit of work here and there at CMU and IIIT. I want to work with you, try to do more object detection research. And he replied immediately. He was like, hey, let's meet. Once you get here, let's meet this day, this time. I go, Yann's in his office, and he's like, hey, listen, do you know anything about neural networks, what I do, my kind of research? I'm like, nope, I've only heard the term neural networks once, and I have no idea what you're doing. And so he went on to explain to me how neural networks work. This was in 2010. Neural networks weren't hot, and Yann had a lot of time on his hands. So that relationship went well. He introduced me to one of his PhD students, Pierre Sermonet, who's now at Google. And Pierre and I was Pierre's understudy. I worked on many things there. I implemented neural networks. Pierre built this deep learning framework called EBLearn, and I was kind of helping out on that. And that made me understand more about how neural networks work, also got me stronger on the engineering side of things. That's roughly how I entered the field. In my 2 years at NYU, we published one paper, and another paper on the work we did got published in another conference. And then in 2012 May, I graduated. I couldn't find a job in deep learning.
Wow.
2012 December was when the whole deep learning boom started. So 2012 May, I was going to go accept a job at Amazon as a test engineer.
Wow. You're like, why did I waste the last 2 years of my life?
It was just so frustrating. I was trying not to give up. I was still super interested in the field, but you have practical constraints, right? Like you're racking up debt, you need to think of all these things.
Yeah.
So in the last minute, I think I had to accept the Amazon offer by Saturday.
Okay.
And on Wednesday, Yann at that day, I don't even remember why I met Yann that day. He was like, oh, where are you going? And I told him I couldn't find a job anywhere else. I'm going to go to Amazon. He's like, oh, just yesterday, one of the companies I co-founded got fresh funding and they're looking to hire engineers.
Oh, wow.
So that was a conversation that happened on Wednesday. I went and gave my interviews on Thursday in Princeton, New Jersey. And on Friday, I signed for Musami. And they were doing music and deep learning on phones.
Okay.
So that was a company that was like
a Shazam kind of thing?
No, it was basically you want to, if someone's playing music, you should be able to transcribe it live onto sheet. And if someone takes a picture of sheet, then you have to be able to play it back for them. So it was like a full cycle. I want to hear, I want to play. So it was like a tool for musicians.
Okay.
And
does that exist for Guitar Tab? Do you have any idea? It should, and that would be awesome.
They do, but it's not a solved problem to decouple when you play multiple notes together. If you play a single note at a time, it's very easy. But if you play like 5 or 6 chords at a time, like decoupling and understanding which of those actually maps to what you played, it's still like an ongoing problem. So I spent time at Musami for a couple of years. We were building all kinds of mobile stuff. I mean, we wanted the whole thing to run on phones. So I was training neural networks on sheet music, and we call it music optical recognition, OMR. And then the company kind of had to fold at some point. In the meanwhile, like while I was at Musami, I also started actively maintaining Torch, which was the deep learning framework that was one of the bigger ones at that time. And I eventually wanted to get out of Musami because we're not sure how the business side of things was going. And then Yann started at Facebook 6 months before that, and they were using Torch as their main deep learning framework, and so they needed good engineers to maintain and develop Torch. And so by the time I was joining Facebook, I was the only maintainer of Torch, so it was perfect. They just got the engineer who will help head this side of things. So I came to Facebook, and there were so many smart people that I just learned so much from. I was also interested in research. And so I ended up going down this path of generative adversarial networks, where we were trying to synthesize images. So the neural network kind of just synthesizes images from nothing. Or
for training, or for what use cases?
This was more of an unsupervised learning use case. So in an unsupervised learning, one of the things you do is generation. And the motivation there is that if you can generate something, you have generally good concepts about how that process works. So the motivation is that if we can do a really good image generation neural network, we can take parts of that neural network and bootstrap other neural networks which are doing computer vision tasks to get better performance. So we could take parts of this neural network and then make it work on a different task, like dog versus cats classification.
Got it.
And without having as much data, you would still get very good accuracies.
Right.
So that's the whole unsupervised, semi-supervised learning motivation. I worked on a few things on the adversarial network side, and then coming to...
And this was back in 2012, 2013?
No, 2014 I joined Facebook.
Ah, got it.
2014, 2015, 2016.
Because the GANs in general have been more, past 2-3 years, I think.
Yeah, GANs have been 2015, 2016.
Yeah.
coming to what I'm going to talk about tomorrow, what happened was Torch has been an aging design in general. It's been 7 years since the previous release of Torch came out. So it was becoming more inflexible. As the field changes, there's this concept where researchers use the tools that they have available to them best, and they push those tools to the limit. And then new tools come that will then, again, make the researchers more flexible and explore new things. So Torch was reaching its limits of flexibility. So we wanted to develop a new tool. And so we worked on it for a year. It started off as an intern project, and then we kept developing it, and we released it earlier this year. It's called Pytorch. And it's what I'm going to be talking about. Tomorrow at Strange Loop, I'll be talking about Pytorch, how it came about, what engineering challenges we faced. Python generally is a fairly slow language, but it's the most popular language for machine learning, for statistics, like all kinds of things. So the most obvious choice to build something in was Python, because all of the users were familiar with it. We have a huge ecosystem.
And the barrier to entry is a lot lower than a C++ or something.
Low. Yeah. You have so many tutorials, and it's very easy to learn and stuff. Yeah. So you had that upside, but the downside was deep learning is one of those high performance computing spaces.
Right.
Every second, every millisecond matters. But Python is slow. Like, how do you make a package that's really fast, but taking a constraint that the users want to use it from Python? So generally, like how we worked around these challenges in various ways, I'm just going to talk about that. Some of the things we did was we moved the most critical parts into C. We made a large part of the implementation lock-free. And
well, let's make sure not to kind of breeze by these topics, because we really wanted to dive into some of these.
Sure.
But, one of the things that is maybe an interesting place to start is, and I've talked about this, I think possibly on the podcast, definitely in my newsletter, just the idea that it's actually kind of interesting hearing your story and how, in a lot of ways, it's like all about timing and mistiming and timing windows and things like that. Like, I think Pytorch has kind of popped up on the scene, if you will, at a time when I think a lot of people had crowned TensorFlow as like the heir apparent to the deep learning framework world, right? And, I wonder if you just hearing your story, if like your experiences with, the timing cycle of machine learning and deep learning, like if that influences your perspective on just kind of the market evolution of, tools and, what you see the opportunity is for Pytorch, and just kind of where you think things are going.
Right. So TensorFlow popped up, was it December 2015, I think? It took the whole deep learning world by a bang, and Google put so much effort evangelizing TensorFlow. I mean, from Sundar Pichai to like pretty much everyone was like, hey, this is TensorFlow. This is what Google's going to be about for the next few years, right? So that, and they have a huge team, and they've been putting great effort into generally making sure everyone are covered by TensorFlow, whether it's a data scientist or a deep learning researcher or like a production engineer. And like what Google did was amazing. They raised the bar for engineering of a deep learning framework so far high. Until then, like if you think about it, Torch, Theano, Caffe, these were the dominant deep learning frameworks before TensorFlow. They all started as one-man grad student projects. And you could totally see that in them. The quality control was really bad. They were not planned properly. If you want to install any of those back in 2014, you would spend a day, maybe more. You'd install that dependency, this dependency. So TensorFlow, it made the engineering bar very high. They were like, we're not screwing around here.
Right.
We want to make the best product out there for people. And they went with a Theano style programming model.
Yeah.
So the Theano style programming model is very, very low level, which means if you want to write something like a connet, a convolutional neural network, then you'd spend writing so much boilerplate code. And also, like the TensorFlow style model, it's called symbolic, which means that like you create a graph and then you run it later. The problem with that is if you want to debug anything, you'd have to use the tooling given by TensorFlow. Like you can't, for example, debug your code by itself. You have to run your model in this other virtual machine, and then you can set breakpoints in that virtual machine using TensorFlow's own tools.
Meaning because it's not standard language X, Python, in the case of Pytorch, it's being interpreted by some virtual machine that knows how to read this graph and schedule execution against this graph. And so the only way to develop, debugging and other tooling for it is via that virtual machine.
That is correct.
Okay.
So the upsides to it are that this virtual machine can be as big or small as possible. You can ship it into phones, you can ship it into anything. The downside is that now where you defined your network was in your Python VM, and you're running your network in a different VM. There's this disconnect. So as a developer, you always have to keep thinking about how the behavior of something in the TensorFlow virtual machine maps back to what you wrote in the Python code. So that's,
anyone kind of on the enterprise side that has some Java experience, knows how different the write once run anywhere is from the practice of needing to know the internals of your heap size and garbage collection strategies and stuff like that.
Exactly.
But doesn't it also give you, or at least the ecosystem, if not an individual developer, the flexibility to decouple the VM from your code base? So meaning, you could write your code using TensorFlow and Python, but have the VM written in, Go or whatever the fast, concurrent, highly concurrent language flavor of the day is, and even port that over to, distributed models or HPC or...
Yeah, so the upside is that the VM can now be written and rewritten in many other things. Right. The downside is that you have to build a whole ecosystem around your VM so that users don't feel depraved by tooling.
Yeah.
And Theano was also like that. That's the whole programming model of symbolic, where you define a symbolic model and then you compile it and then you run it somewhere else.
Right.
The Torch model has always been imperative, which is you don't really have a separate VM. You just declare things, and you don't even you just write 1 + 2 and it just executes it. There's no separation between declaration and execution.
Yeah.
We wanted to extend the same thing to Pytorch. So you just write arbitrary imperative code, and that is your neural network itself.
That also lends itself to, I think, at least in the data science community, there's a lot of popularity and flexibility around Jupyter notebooks as a primary UI. Having an imperative execution lends itself to being able to...
Yeah, you can basically see your execution as it goes. You can print things and all of that.
Yeah.
That's one of the biggest upsides.
Okay.
So while we were building Pytorch, we wanted to continue the Torch model, the imperative style, the dynamic nature of things. And we wanted to build it in a way that it also reaches a very high bar of engineering.
Yeah.
So that's been our core philosophy.
Got it. And so for Google, I think the way most people have interpreted their strategy behind diving deep into TensorFlow is, they foresee this world where AI workloads, whether they're training or inference workloads, are going to drive a ton of compute. Their business model, their non-advertising business model is, heavily geared towards providing compute via the Google Cloud. And so if they can own the model in which, if they can basically own the VM for AI, then they can be the best place to run AI workloads, right? What's the Facebook motivation for investing so heavily in PyTorch and tooling? Is it just not to be, controlled by Google, or is there more to it?
So Facebook's motivation is twofold. For Facebook AI research, which is the 100-odd researchers, and in general for the community of AI, we have a single point agenda at FAIR, which is to try to solve AI. And for that, we're building the best tools out there. And we keep them open just because there's nothing secret to it. We want to build the best possible AI, and we keep publishing about how we're trying to make progress. Our motivation is not really around the business model so much. It's more like, hey, we are trying to solve this very challenging problem. And you see this manifest in various ways in the Facebook product as a secondhand effect. Like, the product teams are not sitting with the AI researchers and saying, how do we improve Facebook as a product? Facebook AI research, the people are independently working on their AI research. But as we build and publish these things, the product teams look at our research and they're like, oh, we can implement this thing in our product in this way, and that's just going to be better product experience for everyone. Like, some examples are, we've had the accessibility interface improve quite a bit recently, about a year and a half ago, where now if you're a user who's blind or near blind, you can view Facebook, like you can basically touch Facebook as you would, and it would tell you what's going on. Before, if you touched a picture, it would just not tell, it would say a picture posted by this person.
Okay.
But if you touch a picture now, it actually tells you, oh, it's a picture where a boy is playing with a cat. And it's very descriptive. And similarly, we're trying to do the same for videos as well.
Okay.
That's one manifestation. Others are where you want to break language barriers. So let's say I have 500 friends. Like, some of them I met in various places and trips. And like, if one of my good friends writes a huge post in Chinese, I still want to be able to know what it's about, right? So we have the translate feature embedded into Facebook, all powered by Facebook research. And you see these manifest in various other producty ways.
And I think you see that evolve as well. Like, if I remember correctly, the Facebook product only relatively recently switched the way they did translation to neural translation. I think there was a blog post on the Fair blog maybe 2 months ago.
Yeah.
So very, very interesting. Okay, so your talk. So kind of walk us through the main points of your talk. It's basically you at the high level, you've got Pytorch. It's inherently built around Python, but you need to find ways to overcome the limitations of Python and kind of how you do that. Was that the main thrust of the talk, or?
Yeah, so it's mostly just a general engineering talk about Pytorch.
Okay.
So I'm going to give like an overview of Pytorch, how it works.
Okay.
A strange loop audience doesn't necessarily know about deep learning computations, right?
More of a developer-focused audience?
Like, a lot of diversity in the programming models we use, and like, strange loop has everyone under the sun.
Yeah.
So,
which is part of what makes it great,
it's
right?
awesome. This is my first strange loop. I've just seen the sessions so far, and like, looking at the sessions lined up for tomorrow, it's awesome.
So, interesting factoid, the guy who founded Strange Loop, a guy named Alex Miller, Strange Loop grew out of a meetup he had here in town called Lambda Lounge. It looked at like functional programming languages, and at a startup that I was at years ago, this was probably 8 years ago maybe, we basically incubated this meetup. They would meet in our office. So I'd be sitting there late at night trying to finish my work and hearing people talk about monads and stuff that I just had no clue about.
Nice. I didn't realize St. Louis had like a big developer community, and like I had like, this is all new to me. So I'll be talking a little bit about Pytorch, start off with, like how to relate it to other things people know. And then a little bit of deep learning workloads, the general challenges, why they're very different from...
Well, let's take those in turn. Like, how should people think about Pytorch and relating it to things that they know?
Sure. Let's say the most common thing everyone knows about is JavaScript, right? So let's look at JavaScript. If you're trying to build a compiler for JavaScript, the things you most care about is JavaScript code, which is very branchy, has a lot of control flow, and it's very, very like cache insensitive. If you're building a very high performance compiler for JavaScript, you will build it in a way that you'll try to optimize for like branch prediction and like try to get traces and do trace compilation, you're tracing, like for example, if you look at Chrome's JavaScript compiler.
V8?
Yeah, V8. It's tracing JIT, or you can look at LuaJIT as another example. It's another tracing JIT, and they will quickly trace through upcoming code, and then if something's compilable, we'll runtime code generate really quickly. And these are all in the order of nanoseconds even, because they're very, very small computations, and they're very branchy. And doing something like loop hoisting or strength reduction, these are the things that would really go well with such workloads.
Okay.
With deep learning, what you do is you do operations on tensors, let's say like n-dimensional matrices. And usually you're doing a computation between A and B, and A and B are not two integers, they're 2,000 integers or 200,000 integers.
So tensor is this n-dimensional matrix,
right.
and when you're doing these calculations, you're basically doing a lot of multiplications of them.
Multiplications, or like any kind of pointwise or reduction, or some kind of convolving-y, like a moving window kind of operations.
Yep.
These are the most common things in deep learning. So when you're trying to make these, like something like this more efficient, you look at how fast you can, how much you can parallelize each of these operations individually. And it turns out almost all of these operations are bandwidth bound. So these operations can run as fast as how fast your memory bandwidth is.
Okay.
Like how fast you can get it in and out of the CPU, because inside the CPU, you're just doing a small multiplication or like, an exponential. But it's still much more expensive to get 200,000 numbers into the CPU and out of the CPU. So the way you would do optimization when building such things, let's say you're building a compiler for these things,
right?
You would try to fuse a bunch of these pointwise operations, a bunch of these reduction operations into an inner loop. And then what you would do is you would get these tensors in. Instead of doing one operation, putting it back out in a result, and doing another operation, putting the result back out, you try to get the tensor in, do 7 operations at once, and then get all like the result of the 7 of them out, because that would make it more compute bound rather than bandwidth bound.
Interesting. So taking a step back, the analogy to JavaScript is primarily to say, you build these high-performance compilation and execution environments by understanding the property of the language that you're working with, right, and optimizing around that. And we can do that here by, in this example, you would take code that is, fundamentally written in a very iterative, serial kind of way, but maybe parallelize or unfold those loops.
Yeah.
I don't know if that's the right way of thinking about it, but
say tile the loops.
What's that? Tile the loops?
Tiling. It's called tiling because you can break the computation to, I have 200,000 of these. Okay, I'll just make tiles of 20 and send them to like 20 different processors.
Okay. Interesting. Oh, that's very cool.
Especially with GPUs. With GPUs, you have 3,000 cores on your GPU.
Right.
So you want to break this computation down and feed those into all the separate processors,
right,
and then get the results back.
But they don't fundamentally change the bandwidth issue.
They don't. The bandwidth issue still exists. At least. Yeah. So I'm going to be talking a little bit about the JIT that we built into Pytorch. We built a just-in-time compiler. It's also a tracing JIT, but it's of a very different kind. Our tracing is not in the order of nanoseconds, it's in the order of microseconds.
Okay.
But that's completely fine because general deep learning workloads are in the order of milliseconds.
Right.
And the kind of optimizations classes we write as well are, as I said, more like fusion and batching. By batching, I mean, let's say you do computation X, Y, Z. But between computation X and Z, they're shared operations. Let's say X also does multiplies and Z also does multiplies. So the tensors involved in X and tensors involved in Z are very small. So what you do is you create a multiply operation, combine the tensors that are involved in there, and then after the result comes out, separate them out. Mm-hmm. So this is called dynamic batching. Yeah, so we've been writing this JIT that's very new for us, as in not many people have worked generally in this direction. TensorFlow is building one called XLA. It's a compiler. And the kind of optimizations they're doing as well are very similar in nature. Like everyone's exploring now these, like how to make tensor computations faster. We're just taking the just-in-time approach, and they're taking the ahead-of-time analysis approach.
Mm-hmm. And I think of JIT, and this probably comes from really JavaScript, as something that is more relevant to interactive types of workloads than batch. But deep learning is primarily a batch workload, at least the training part of it.
Depends on how you see it. Like, we want to keep the interactiveness, because remember what we talked about. People like to keep that interactive Python-y, IPython notebook style programming model. We want people to keep that flexibility.
But that's not really where you need the super high performance, is it?
No, that's people do interactively. They're programming 8 GPUs. Like, this is this is the norm in deep learning.
Okay.
So you're backed by your super powerful GPU.
Okay.
And I'll talk a little bit about this in the talk tomorrow, about how your Pytorch tensors can just be transferred to the GPU and you operate on them. And all the operations are now being done on the GPU with very high performance. But you're doing this in a very interactive way.
Okay. It is a little bit of a mind shift for folks that have been kind of immersed in a TensorFlow-oriented or a batch-oriented world, where you kind of create this job, you send it off to the cloud or wherever to train, and then you check on it in a few days.
Yeah. We are the worst nightmare for hardware developers. Because they're all building solutions around, let's say you build this model beforehand and then you give it to our hardware, which, let's say it takes 30 minutes, but it will map your model in the most effective way to our hardware. And after that 30 minutes is done, if you pump any images in or any inputs in, it'll be like super fast. And we're like, well, that's kind of dumb in our model. Like we'll give you a different model in every single iteration. What are you gonna do about it?
Right. Interesting. So, speaking of hardware and hardware developers, I don't know if this is something that you're close to at all, but Facebook also is very involved in this OCP, Open Compute project.
Yeah. I was involved in the Big Sur and the Big Basin.
Oh, were you?
Yeah.
Okay. So do you see, as I understand it, OCP has primarily been oriented around kind of off-the-shelf stuff, like system architecture as opposed to, board level architecture or anything like that. But do you see a future where OCP takes on like this bandwidth problem to try to make hardware that's more suitable for these kinds of workloads, or are those other people's problems?
I think OCP is one of those huge industry-wide efforts, right? Mm-hmm. I think it's totally possible that under OCP you'll get something that's like a custom ASIC. Mm-hmm. And I'm not sure how that will happen in general, because there's so many players and so many people who can contribute to OCP. Mm-hmm. Just 2 days ago, I think, or yesterday, NVIDIA released an open spec with Verilog files and HDL files of a chip that does convolutional neural networks. Like a high-performance convolutional neural network-based thing. It's based on...
I think I saw the headline for that. It's like, this is NVIDIA's TPU.
Right, I mean...
That was the clickbaity headline, at least.
They basically put it out there. You can take that...
And the Verilog and HDL is basically the code for fabricating these chips.
You'll have to still remap Verilog into the actual process you're manufacturing under. But that's a mechanical process that usually, you usually give your HDL files to someone, and then they'll spend, their company will spend remapping whatever you have to the process most effectively. But it's a fairly mechanical process at that point. So now NVIDIA just released this open chip.
Yeah.
And that's totally one of the candidates, for example, for open compute. Open compute is all about, everything is open.
Right.
You can reproduce
Everything's open. Let's compute.
Own, right? So I think we're still not sure about what's going to come into OCP in that direction. I personally don't know the details.
Right.
So we'll see. We'll see how it goes.
Okay. So You also mentioned that parts of the Pytorch engine are written in C. It makes me think a little bit of like in just kind of the regular Python community, there's, if I'm remembering correctly, there's like PyPy and Cython and all these different implementations of the Python interpreter. Is it the same general idea there?
Not at all. PyPy is a replacement for the default Python implementation, which is called CPython.
Okay.
So Python is a programming language, and they have a base implementation of that programming language that the language developers develop on, which is called CPython. It's
Right.
written in C. And if you type Python into your desktop, usually that's what it is.
CPython.
And Cython is just a very cute way of writing extensions to Python, like to CPython mostly.
Okay.
PyPy is a replacement interpreter for
CPython.
Python. For CPython.
It's written in Python.
That can interpret Python. I'm not sure what it's written in, but I don't think it's written in Python.
Okay.
The implementation is probably not in Python.
Okay.
PyPy is a just-in-time interpreter for Python. It's probably written in part assembly and part C or whatever.
Oh, okay. Okay. So the idea being the significance of it is not its implementation, but just in time versus not just in time.
Yeah.
Okay.
Pytorch is just a CPython extension. Like all the C bits we have are, the equivalent you can find is NumPy. NumPy is 90% written in C.
Yeah. Okay.
But it's a CPython extension. That is, it's not an independent C library that you can run. It's like heavily integrated into the CPython API and stuff. So Pytorch is just like a Python extension.
Okay. But there's recently been an announcement of, one of the first, I think, kind of broadly publicized Pytorch wins, if you will, is like Fast.ai deciding to rewrite all of their courseware into Pytorch.
That was a very pleasant surprise.
Was it?
As soon as Pytorch came out, I think they've tried it and they found it really effective, especially for teaching and the barrier of entry. Yeah. So they've switched over to Pytorch from Tensorflow, and we're supporting them in any way we can.
Yeah, yeah. It's interesting. I think if there's anything that this community benefits from is options, and especially options that, have major, both major companies behind them pushing them forward, but also that are open to community engagement and community contributions. And so it's definitely great to see, from a kind of industry observer point of view that, we've got, what's starting to look like a second kind of really strong contender at a time when, again, I think a lot of people said, oh yeah, it's just, it's TensorFlow. So congrats for your part in that. And thanks so much for taking the time to sit down with me.
Oh, my pleasure.
Appreciate it. All right, everyone, that's our show for today. Thanks so much for listening and for your continued feedback and support. For more information on Soumith or any of the topics covered in this episode, head on over to twimlai.com/talk/70. To follow along with our Strange Loop 2017 series, visit twimlai.com/stloop. Of course, you can send along your feedback or questions via Twitter to @twimlai or @SamCharrington, or leave a comment right on the show notes page. Thanks again to Nexosis for their sponsorship of the show. Check out twimlai.com/talk/69 to hear my interview with the company founders, and visit nexosis.com/twiml for more information and to try their API for free. Thanks again for listening, and catch you next time.